In the last two episodes of C++ versus Rust, we have talked about deferred functions, and we have mentioned that the deferred functions mechanism would help us avoid deadlocks. Well, we won't be able to fully prevent deadlocks using this mechanism, but let's look why deferred execution helps with deadlocks, and in general, why does it help with performance. So this is our NodeGraph. We start the execution of the NodeGraph by putting a value into the source node. When we do that, we call the function loadValue. When this function runs, it locks the output pin of the source node. And we put a value into that pin, so that's a write operation. So we lock this pin for writing, because we use read-write lock. This lock has capability of locking for reading and writing. If at the same time some thread approaches this pin and tries to read the value, it will have to wait. So now we've finished setting the value on the output pin of the source node, and we exit the function. When we exit the function, the read-write lock is unlocked. Because the way the read-write lock works is, if this is a scope, right? This is where we acquired it, and when the scope ends, this is where read-write lock is unlocked. So our code existed somewhere in between these two barriers, okay? So lock, unlock, meaning that the code here would execute without this lock, as well as code here. So this scope for read-write lock, when we call either write or read method of read-write lock, will be the line of code, or it will be extended if we assign it to a variable. Let me show you an example in the code. Let's look at this sendData method of this output pin. What we can see here is that for the input pin, we acquired the write lock. So what is the lifetime of this write lock? So write gives us the guard, and the lock will live for as long as this guard is living, okay? So we are accessing the pin member of the graph node input pin, and on that pin we call setData. Now, the way it works, we locked this graph node input pin for writing. So now we have, this dot is giving us a mutable reference to that pin, okay? This means that this setData can be called because it requires a mutable reference to self which is graph node pin. And this, as you can see, there is no lock here. We just assign a new value to the member variable. But this is called for a mutable self, and that mutable self is only possible to be mutable when we acquire the write lock on the read-write lock, right? So the write lock gives us a mutable reference to an underlying object. So that is internal mutability guarded by the lock. So how long does this lock last? It will last for as long as this whole call of the setData, okay? So if we go to setData, everything that we do inside of this function will be done under that lock. And if that function was to lock another object, we would have to be very careful, because then we would have two locks. How to avoid locking two objects at the same time? Let me show you an example when that would happen. So this is the previous implementation, which was not using deferred functions. And in this implementation, we acquire a lot of locks at once. Just look at this process forwards method. We acquire the lock for the input pin, but this lock is released after this line, right? At this line, we don't have this lock anymore. So this one line isn't an issue, right? We're not calling process forwards under the lock. Are we not? Are we sure? So let's look at this process forwards method of this transfer graph node. We acquire a read lock on the input pin, and that is a lock. Process forward method is not taking the mutable self, it's taking immutable self. However, let's see how it's called. And the function is called from the output pin. In the output pin, we acquire a read lock on the pin that is connected to this output pin. But this read lock lasts only the lifetime of this single line of code. It doesn't go into this line of code. Because this read lock is temporary lock guard, and it is destroyed after this line. So when we call process forwards, we're not locking anything anymore. However, are we sure this is the case? Let's check the process forwards again. How about this line of code in process forwards method of transform graph node? Here we acquired the read lock on the output pin. And after unwrapping, we got the lock guard, which allows us to read an object. And we call propagate forwards. We will be holding this lock during propagate forwards call. We're holding the lock. This propagate forward method will be called under this read lock in full. This read lock will expire in this line of code. It will be still present inside the call of propagate forwards. And we can see we acquire another lock inside of propagate forwards. So we're acquiring two locks. But we're holding this lock on this output pin while calling this method. And this input pin read lock, it will last until end of this line. However, it's still acquired under this other lock that we acquired to call this method. And now we're calling node process forwards on the node of the connected pin. In our graph, it is the target node that's connected to the transform node. And process forwards of the target node doesn't actually do anything. But imagine there was another transform node connected. If it was a transform node connected to a transform node, then now we're locking the output pin of this second transform node. So we're doing that under the lock of the output pin of the first transform node, and now we're locking the output pin of the second transform node. So we're doing a lot of locks under already existing locks, right? We're acquiring more locks and more locks. We started from the source node, and we can see that the source node holds a lock to its output pin while calling propagate forwards. In source node, we grab this lock for the whole duration of process forwards. The reason is that we want to do these operations in one transaction if possible. So we hold on to the lock on this output pin on the source node. And we know that the transform node will be locking pins when we call process forwards on the transform node. First, it will lock its input pin to read the data. Then it will unlock it, but it will lock the output pin to put the data on that pin. And then it will lock this pin for reading and propagate forwards while holding this lock. And that will go to our target node, which doesn't do anything in process forwards. But if it was another transform node, that other transform node would start locking its input pin and output pin. So we would have a lot of locks acquired at one moment of time. And that lock on the source node output pin would last a very long time. So the whole branch of execution in this graph would be locked. And that's not great. So with the deferred actions, we lock the output pin of the source node to enumerate over the pins that are connected to this output pin and to access the nodes of those pins. But we tell those nodes to process forwards, which gives us back the deferred actions. So we don't lock those input pins anymore because we don't have to. To obtain a reference to the owning node from the input pin, you don't have to lock the input pin of the node. Not in C++. We do lock this input pin in Rust. So in the Rust version, in order to get the node of the pin, we have to lock the pin. But in C++ version, we can use unguarded pointer and get node. We can use unguarded pointer because, as I have explained in previous video, the nodes and pins in C++ have a different memory layout than they do in Rust. And that's for efficiency reasons. But at the same time, we can access the unguarded pointer without locks, because we know that the getOwning node returns a reference that cannot be changed. When you define a member variable in C++, which is a reference, it can only be assigned in constructor. It cannot be changed. So yes, we would lock the input pin of the transform node in order to get the node, the transform node, in Rust. But in order to process forwards from that node, we wouldn't hold on to that lock. This lock disappears after this line of code. So we lock this input pin of the transfer node to obtain this transfer node. But then this lock disappears, and we ask this transfer node to process forwards. And that will lock the output pin of the transfer node. So in our Rust code, we lock the input pin of the transfer node. Now, in our version of the NodeGraph with deferred execution of the nodes, we only create here a deferred action. We do not lock the output pin of the transfer node. And we actually unlock this pin after returning this deferred action. We can see here that we acquired a read lock on the input pin of the transfer node to get the transfer node. Get node will give us the transfer node in this case, and then on that transfer node we call process forwards. But in this case, propagate forwards returns an action. We create this action by calling defer parallel of actions, and actions is a vector which is a result of mapping all the connected pins to this output pin into actions, right? We call process forwards on each node attached to those pins to get an action to process forwards. So you can see that here process forwards is returning an action. It's not locking anything. We only get the pin reference, we increment reference count on it, and we move that copy into that deferred action to keep the pin alive. And then inside of the deferred action, we acquire some lock. This is process forwards for the transfer node. It returns an action. It is a deferred action, and all the necessary locking happens inside of this deferred action. We just add references here to the input and output pin, and we move those into this deferred action, as well as this helper function. None of this code will be executed under the lock from the source node. So we receive those deferred actions here while holding this lock. But now we're returning this parallel deferred action to the user, and we're not holding any locks anymore. Now the additional benefit is that the user can actually call those parallel deferred actions in parallel. We can see that if user uses rayon policy, those parallel actions will be executed in parallel. So we're not only unlocking this output pin of the source node to propagate forwards, but we also open ourselves a door for parallel processing of this graph. I can take this action, run it on one thread, and it will go to this node and propagate forwards. I can take this action and run it on the other thread, and it will go to this node and propagate forwards. And we have two parallel threads, thread 1 and thread 2, two threads. So we have parallelized this node graph using this very simple technique. Additionally, there is no latency introduced, or shall I say almost no latency. So the first of those parallel deferred actions will be probably executed in the same thread as I'm applying my policy. So there is no delay. And the second action will be queued into the other thread that's probably running in a pool and will execute this action immediately. So there is a latency of the other thread picking up this action. And then, when the threads propagate forwards, this will produce new deferred actions. These are the continuations. But the continuations will execute immediately. They do not have any latency. Just look at this. This is our deferred action execution loop. Here we have applied an action, and it returned a new deferred action. And we're doing the next iteration. There is no delay. The action that was returned is executed immediately. So this action will be executed immediately without any delay after this action is finished. And this action will be executed immediately after this action is completed. There is no delay whatsoever, no latency, zero latency. There is zero latency between when this action finishes and this action starts. There is a little overhead of some code that needs to execute. So this loop, for example, has some code. This condition needs to be executed. This lambda needs to be created. And this lambda. But lambda is just a structure. We're just allocating a structure and filling in the fields. Those variables will be captured in those lambdas. This lambda captures output pin 1, and this will be the member field of this lambda, 1 and only. And this lambda captures input pin and output pin 2. So just 2 fields. It will be a structure with 2 fields. That's it. And we just return this structure back. It's not that big, right? So the execution of deferred actions shouldn't affect the performance that much. So we have an elegant way of running this graph in parallel and at the same time reduce the amount of locking. We only ever lock the pins of the node in consideration, or the output pin of the node and the input pin of the connected node. So we have the situation that we lock at the same time 2 pins. It means that we could run into deadlock, because if we lock those in opposite order, so let's say the thread number 1 tries to lock this pin and then tries to lock this pin. But thread number 2 has already locked this pin and is trying to lock this pin. And this is a deadlock. It's not going to happen in this case because our second thread is locking pins on a different branch of this graph. Those pins maybe. And our first thread will be locking those pins. You may say, if this is the only thread that is accessing those pins, maybe we don't need to even lock them. That will be unsafe, right? There can be always some other thread trying to access those pins. Let's look what happens if we're propagating forwards on one thread, and then we also started propagating backwards, from the other thread. So the thread that propagates backwards locks these pins first and tries to lock this pin. And the one that tries to propagate forwards locks this pin and tries to lock this pin. So the deadlock is possible, right? Even though we have those deferred actions. But the deferred actions allow us to avoid locking those pins. And if there are more pins here, we also don't lock them. At any given time, we only lock 2 pins, thanks to deferred actions. Without deferred actions, we would execute this whole branch at once, and we would lock all these pins, or even this one. If we propagate backwards, you would need to be careful how we lock pins, because we'll be locking this pin, then we'll be locking this pin, then we'll be locking this pin, then this pin, and then we have to return back. So of course, the deferred execution solution is much more dynamic, and it prevents too much locking. It prevents contention of locks. It enables parallelism. If you lock too many locks, your parallelism can serialize. For example, if you run one thread propagating backwards and another thread propagating backwards, this pin would need to be locked by both threads, so there's a contention point. In this simple graph, the deferred action might be going from transfer node to source node on both threads if there's 2 threads executing in parallel, propagating backwards. And they may meet at that pin. So the pin needs to be locked by one of the threads so that the other thread can wait. If it's read for reading, then both threads can read it. However, if this graph was more complex, if there was more connections coming out of the pins, there'll be more points of potential contention. So with deferred execution, we don't lock those pins unnecessarily. So the deferred execution does not fully prevent deadlocks, but reduces the chances of deadlocks, reduces the contention on the locks, makes the locks more manageable. Just look at this situation. If we have these 2 pins, both locked, and we don't lock any other pins at the same time. So in our scenario with deferred execution, we only lock maximum 2 pins at once. In that case, we could always control the order in which these pins are locked, or add them into a lock set. we always have 2 pins, and we know exactly which 2 pins we are locking at the moment. So we could control it better. However, if our execution is not deferred, if it's synchronous, then we locked a lot of pins on our way, and we have completely no control over what we're locking, especially when the graph is more complex. So the deferred execution allows us to have more control over our locks, reduce the contention on the locks, and as well introduce parallelism at no cost, because those deferred actions can be then executed on parallel threads. You see, when the action returns an action, the next action is executed straight after this action. And that just creates a sequence of actions to be executed. But in order to support parallelism, I have this special parallel action. It's a vector of actions. So that now, by seeing parallel, we know that those actions, they're independent and can be executed in parallel, as opposed to sequential. A sequential could be just replaced with an action that returns next action to be next action in the sequence. It could be a single that will return a single that will return a single. But there is no need for that. We can have better control if we call it sequential. But single returning a single, that cannot be parallelized. That's why we have parallel. This way we have a set of actions, and we know that they can be executed in parallel. And our rayon policy takes advantage of that. It executes those actions in parallel. Same as a standard policy in C++. It will also execute those deferred actions in parallel. And we're using standard library execution policy parallel. You get this out of the box with standard library. So there is no need to manage your threads at all. You can use standard library parallel execution. All you need to do is wrap the things that need to execute in parallel into lambdas. Perhaps these lambdas in C++ aren't the prettiest. The return statement, the semicolon, the captcha list, right? Let's compare it to Rust. This is the Rust version of the same function. In this deferred action, we just say input pin read, unwrap, propagate forwards. No return statement, no semicolon. We can write this, we can say return and semicolon. Rust allows that. But I think this isn't the prettiest way of writing Rust code. Especially that this version is simpler, shorter. So yeah, Rust lambdas look prettier. You can see that we define here a sequence of 2 deferred actions, same as here. And here from the middle we return a deferred action, and that return deferred action will execute as nested action of this deferred action, but after this deferred action finishes. So the nesting happens after exiting the parent action. We're still in the same stack frame. We're creating a new stack frame in which we execute those nested actions, but we execute them after this parent deferred action is executed. Those deferred actions all have to finish before we go back to the parent stack frame and continue with the next deferred action in this sequence. So this is quite clever, right? You can control the flow, whether it's sequential or parallel, and you do have this nesting of actions. And nesting doesn't hold the context of the parent action. Unlike in regular function calls, when you call a function from within the function, that parent function, its old frame resides on the stack, and that new function that you're calling is on top of this. Whereas here, once this deferred action finishes, then we create a new stack frame when we run those nested functions, right? So it's more like a coroutine way of doing things. We may explore how to convert this code into coroutines in C++. That would be cool, right? Because this essentially is an implementation of a coroutine with lambdas. So this is an implementation of coroutine, of asynchronous code. And asynchronous code works in that way. this deferred sequential can be equivalent to an asynchronous function, and some instructions of this function execute until the first await. So this will execute, and then we await on this thing, because this thing returns more actions. The context from where we created those actions needs to await for it. But the whole asynchronous await, the way it is implemented in languages, as far as I know, is exactly that way. You have, callbacks. So the first part of a function before await, it's one block of code that will execute. Let's call it lambda. And then there is a wait on something. So that's something that we're waiting on is another block of code that executes somewhere, another lambda of some kind. And then there is code after that await, which is another, lambda, let's call it. And this one here, right? So we execute this one, then we execute the thing that we are waiting for, because this returned an action. And after that, after the wait, we execute this one, right? So this is how asynchronous tasks can be implemented. Depending on the implementation of the asynchronous feature in different programming languages and libraries, this can be implemented as this kind of callbacks, or some implementations can actually store they can store the CPU state and restore it later, right? They can do that. These are two different, maybe approaches of how to do that. In asynchronous function, if you were to define a variable within the scope of that asynchronous function, the lifetime of this variable is the whole scope until the end. If this sequential was equivalent to asynchronous function, then if it was an asynchronous function, this x that I just defined here would live until this line. Obviously, this x wouldn't be bound to this one scope. I don't know if I'm explaining it well. So that has some consequences. So let's say we want to rewrite this in Tokyo. Let's say we want to create an asynchronous code here. Let's say this function propagate backwards is asynchronous, and we await on this propagate backwards here. If we were holding lock while calling process backwards, we're still holding that lock. So with asynchronous programming, you wouldn't achieve the same benefits as we do here in our deferred execution. And we wouldn't be able to control the parallelism, how our actions are executed. We would have asynchronous functions. We would just await on their execution, and then the engine would execute them in a way the engine likes. If engine wants to execute them on a thread pool, it would use a thread pool. If it wants to use an IO loop on single thread, it will use IO loop on a single thread. And we have no choice of deciding how it is executed, unless there is some plugin in the engine that executes that to control that. This mechanism is much simpler. You just return lambda, and then the user decides what to do with this lambda. Is this lambda something that I want to run right now? Is this lambda something I want to run on a different thread? Do I have a special thread for this lambda? So, with these deferred actions, you as a user receive those actions that you can do whatever you want with them. You can run those actions at any time. You can even cancel them. You simply cancel them by never running them. This gives you a lot of control. But we can agree the code doesn't look as pretty as asynchronous code. Nevertheless, we will explore how to achieve similar results with Tokyo in some future episodes. And we'll also explore how else can we execute those deferred actions, because now we're using Rayon. And in case of C++, we use standard library. So we don't actually control how those actions are executed, except that we just say execute them in sequence or parallel. But we could put those actions into some queue or queues. We could start our threads ourselves. And now we would have a chance of deciding how those queues are implemented. Maybe we want to use some channels in Rust to implement those queues. Or maybe we want to use some ultra-low latency rigging buffer in our C++ implementation. What would be the latency between threads? So we have received these two deferred actions when we called on the source node process forwards. Or maybe we call process backwards on the target node. But we have those two deferred actions. Right now, we just use standard library to run them in parallel. But we could put them into some other mechanism to run them. Depending how fast the dispatching is in this mechanism, if it's a standard queue with a mutex and conditional variable, that's an unbounded queue. Or if it is a bounded queue using semaphores, what will be the performance? How about we use ultra-low latency ring buffer and put those into this ultra-low latency ring buffer? How much latency we would introduce if we did that? What is current latency? Because now we tell the standard library to run this in parallel. Perhaps the first of those items runs on current thread and has no latency. But what about the second one? What is the latency of the second one? How fast the background thread can pick the second one? With ultra-low latency ring buffer, maybe it's instant. So we will explore this avenue in some next episode. And we'll also explore the avenue of asynchronous programming. We will use Tokyo and asynchronous functions. But we know that if we lock this pin, then we go to the connected pin, ask the node to process forwards. How do we make sure that the continuation is executed later, that we release this pin? Can we achieve that with asynchronous code? Can we run this code after leaving this code? Can we leave this lock? Just to explain once more, there is a function scope of a parent function that is calling our function. Inside this function, we acquire the lock, and it lasts some amount of time, maybe the whole scope, maybe less. But under this lock, we're calling another function. And this is another function. And you can see during the lifetime of this function, this lock is acquired. If this function is asynchronous, it doesn't help because this lock is still acquired. This lock, we cannot make this lock last, let's say, only this amount from the inside of this function. This function cannot unlock it. If it's asynchronous, it doesn't help. So we will look how to achieve this similar result as we achieve with deferred execution. How does it compare to deferred execution? We have some parent function, and this function is acquiring some lock. And inside this lock, we return a deferred action. And this deferred action is maybe even returned from this parent function. Now, this function was called from some other parent function, maybe from main. And we received this deferred action here. We're not holding any locks at this stage. We can just execute this deferred action without locks. So this is very interesting, right? How do we achieve the same goal? It's perhaps asynchronous programming. Is it possible? So that is a topic for another episode. All right. Comment, like, subscribe, and stay tuned for the next episode. Thank you.